Oh, hey there, you again. How was that quiz from last week? Did you do well? Maybe, maybe not. Well, if you didn't do too well, just remember there are many, many more quizzes to come. So you'll have many more chances to do very well on the quizzes. So even if your quiz wasn't, or your quiz score wasn't what you had hoped, whatever you do, just don't worry. Okay? So let's begin with the second recitation. 1.3.15. Is this expression, the negation of Q and P implies Q implies negation of P, a tautology? And specifically, it wants us to determine this using equivalence laws. So we're not allowed to use a truth table, right? A truth table would be too easy. You would just have to look at all the rows. If all the rows had a 1 in it, you would know that it's a tautology. But we're not allowed to do that. So how do we begin determining whether this expression is a tautology or not? Well, we begin with the expression itself. Let's think about what kind of law we could use to convert this expression to something more simple, right? We're always looking to simplify things so that we can try to show that it is just equal to T, which stands for tautology. Okay, so the easiest thing we could do is to convert all of the implications to or operators, right? That's definitely the easiest thing we could do. So let's use the implication law. Let's say that this expression we're given is equivalent to the following, right? So all we did here was we converted this implication and this implication operator into an or operator. Now remember, when we convert an implication, we have to change the left-hand side of the implication to a negation. So if we have P implies Q, this is equivalent to the following: not P or Q. So right here, P implies Q would be converted to not P or Q, which we've done so here. This entire expression here is the left-hand side to this implication operator here. So this entire expression will become negated, right? And we know this because it has parentheses around it. So that's how we know how far-reaching that implication goes. So that's this negation symbol here, negating everything that comes before this implication operator. Then we change that implication to an or. Finally, we're not done yet. We have to also write which law we used. So because we converted the implications into or operators and then negated the left-hand side, we used the implication law. Right? Be sure to always mention which law we used at every step of the way. So that's just step 1. What would step 2 look like? Well, we want to simplify this expression further. Let's use De Morgan's law. We see this negation symbol out here. Because it's around a set of parentheses, we can apply the negation symbol to everything within the parentheses. It's kind of like in grade school, right? What's 2 times 3 plus 4? We take the 2 and we multiply it across by the 3, and we multiply it by the 4. It kind of works the same way. If we apply the negation symbol to the negation of Q, what do we get? Well, we get the negation of the negation of Q. Now we know by the double negation law that that's just Q. So let's write Q. We apply the negation symbol to the AND operator, it becomes an OR operator. We apply it to this set of parentheses, and we get the negation of P or Q. We could go further, but we're not going to do that just yet. Finally, nothing happens to the or not P because that was outside of the parentheses that this negation symbol was affecting. So how many laws did we use? We used De Morgan's law, and we also used the double negation law. Okay, Now, the next step. We can't really go any too further here. So instead, let's start to move things around. Let's use the associative law and the commutative laws to regroup some things here. Obviously, we don't really want to change this quite yet, so let's leave that. We have the negation of P or Q. Or let's take this negation, or let's take this Q, bring it to the right, and pair it up with the negation of P. Moving the Q to the right works a lot like this. If we have 3 plus 2, isn't that the same thing as saying that 2, right? Isn't that the same as 2 plus 3? It's the same thing. We use the commutative law to commute our symbols, to move them around. So we're going to write Q, or we can do this in any order actually. We're going to try to pair it up with the same order we have right here, which would be the negation of P or Q. Now, let's use the associative law to regroup things, right? The associative law comes from the word associate, which means to group. And by that, we're just going to add some parentheses. So we're going to add some parentheses around the symbols because it matches with what's here. And we're done with this step so far. We used the commutative law and the associative law. Okay, so we're pretty much done here. We have this expression here, and we know by the negation law that the negation of something or the thing itself must always be true. So we have the negation of an expression or that same expression without the negation symbol. By the negation law, we know that's always true. Therefore, this is a tautology. And don't forget to write the equivalence law we used. We begin with the next problem, 1.3.20. Show that the negation of P XOR Q and P by condition Q are logically equivalent. When we get a problem like this, we can begin any way we want. So we can either begin here with this expression and work our way here, or we could begin with this expression and work our way there. Either way works. I'm going to begin with the negation of P XOR Q. And you don't have to memorize this. It's probably in one of your recommended texts somewhere, but P XOR Q is equivalent to the following. Right? And then, because there's a negation symbol around the parentheses, we're going to add some parentheses here and put a negation symbol out there, right? But P XOR Q is equivalent to negation of P and Q or P and not Q. And that's just something that you don't have to memorize. In fact, there are many different equivalences to the XOR operator, this is the exclusive OR. Our law here would just be the definition of XOR, right? So we didn't really use a law, we just kind of used the definition of what this symbol translates to, which I guess would be a law in itself. So, from here, let's use De Morgan's. Let's apply this negation symbol across this expression onto the OR operator and onto this expression here as well. This gives us the following: the negation of P and Q and the negation of P and the negation of Q. We used De Morgan's law. I'm going to write DEM. Just know that I mean that to be De Morgan's law. You should probably write De Morgan's law on any quiz or exam or homework you're given. Please don't write DM. I'm just writing it to shorten things up, but I guess if I have to explain it, it's not really shorter, so, okay, anyway. From here, where do we go? We can use De Morgan's law again. Let's take this negation, give it to the negation of P, give it to the and, give it to the Q. This negation symbol is going to be applied similarly. We get the negation of P or Q, and the negation of P or the negation of Q. Let's also throw in the double negation law. And on that same step, let's convert the negation of Q to just a Q, and the negation of P to just a P. From here, it gets a little tricky. We kind of have to think about it. But oh, I'm sorry, this should be a negation symbol as well. You kind of have to think about it, but the solution to this problem is to actually convert both of these OR operators to implication operators, right? Because we have to get a double implication somewhere. So let's use the commutative law to move things around first. Let's say the negation of Q or P, and we keep this expression on the right the same. We used the commutative law to do that. All we did was switched the P and the not Q, we switched their place. From here, we have the negation of Q or P. We know that we can convert that to an implication. Q implies P. We just negate the left side of the OR operator and then turn the OR into an implication symbol. And turn the negation of P into a positive P. From there, this also you don't really have to memorize, but this expression over here, it can all be simplified to a biconditional operator. That is P by condition Q. And that just comes from the definition of the bicondition symbol, which itself is an equivalence law. Somewhere in your recommended text and reading, but not something you'll have to memorize. Okay, and then we're done. Next problem is actually an example. Example given in the textbook. It's example 1.4.26. It reads, 3 sentences. The first 2 are premises, and the third one is a conclusion. All lions are fierce. Some lions do not drink coffee. Some fierce creatures do not drink coffee. And it wants us, or the example, what the example does is it converts three sentences into predicates. So first we have to decide what our domain is, right? What is X? What are we talking about here? Clearly these sentences are describing something. That something is our domain. Would our domain be lions? Well, no, because this third sentence does not have any lions in it. It has creatures. But couldn't a lion be a type of creature? So a lion describes a creature. So a lion could be one of our predicates. Maybe creatures is our domain. So X is creatures. And then let's create some predicates to describe those creatures. Respectively, P of X means X is a lion. Q of X would be X is fierce. R of X would be X drinks coffee. We could have named our predicates anything. So this could have been a Z, it could have been a C. I think C would have made more sense because it's all about coffee. But either way, this is how the example goes. We are describing creatures in all three of them. And with these three predicates, we should be able to represent these three sentences without any gaps, right? We have coffee. The creatures could drink some coffee. That would be used by the third predicate. Q, they're fierce over here. The creatures are fierce, so that would be described by Q. P, they're lions. So the creatures are lions, and that would be described here in the first two premises. So now we have to put things together using various laws. The first premise reads, all lions are fierce. Well, we have the word all. And when we have the word all, we know it's a universal quantifier, or we have to use a universal quantifier because it's true for all creatures which are lions and are fierce. So for all x, that is to say, all creatures, P of x, if the creature is a lion, this implies Q of x. This implies that the creature is fierce. Usually when we have the word are or is, sometimes is will also be used, we know that we have an implication of some sort. Okay, so the next premise, some lions do not drink coffee. Well, again, there's a key word there, some. When we have the word some, usually that means instead we're going to be using the existential quantifier. There exists some creature that does the following. So let's use the existential quantifier. You can remember it's the existential quantifier because it looks like a backwards E. So there is some creature, maybe even some creatures, where that creature is a lion and does not drink coffee. Not drinking coffee is the negation of are. So you might be wondering, why are we not using the implication here? Well, when we have an existential quantifier, we do not use the implication symbol. Instead, we use the and. Also, we don't have the keywords are, and we don't have the keyword is, so chances are it wouldn't be an implication anyway. Next, some fierce creatures do not drink coffee. We use an existential quantifier because we have the word some at the start. There exists a creature, there exists an X, which is fierce, X which is a fierce creature, and does not drink coffee. And you could represent these three sentences with these three mathematical statements. I'd like to preface this question with letting you know that I'm really sick of these word problems because they're starting to really cramp up my hand. Express statements using quantifiers, then form the negation of the statement. So, no negations to the left of a quantifier. Remember, a quantifier would be like the universal quantifier or the existential quantifier. Next, express the negation in simple English. Okay, so not too bad, right? Some old dogs, let's begin with the first one. Some old dogs can learn new tricks. Remember, the first thing we always have to think about is what is our domain? Well, there's not much to go, right? It wouldn't be creatures because, then we would have to describe that creature as a dog. So instead, I would say dogs is our domain. We're describing dogs here. X is dogs. Then let's define a predicate. Let's say that T of X is the following. X can learn new tricks, right? Because that's kind of like the action going on here. We're saying that the dogs can learn new tricks. That's our predicate. Therefore, because we have the word some, the keyword some, right now we have the following. There exists an X such that T of X. There exists a dog, or there exist some dogs, there's at least one dog such that that dog can learn new tricks. Then it asks us to form the negation of that statement. What is the negation of this statement? Well, it would just be that very thing with the negation symbol in front. However, it asks us that no negation be to the left of the quantifier. So what do? Well, we kind of do what we did with De Morgan's law, in that we apply the negation across everything. So we apply the negation to the existential quantifier. We apply it to the T of x predicate. What we get is, for all of x, the negation of T of x. And how would this read in English, right? It wants us to express the negation in simple English. Well, it would read like this. Every old dog is unable to learn new tricks. Right, so x is that we're actually, our domain would be old dogs. Hopefully that still made sense though. Our domain is old dogs. Every old dog is unable to learn new tricks. Colloquially, like, how a normal person would say it, no old dogs can learn new tricks. We could have also said, every old dog is unable to learn new tricks. Right, so there are many ways to express this in English. Those are just 3 of them. All right, let's go on to the next problem. No rabbit knows calculus. And again, we have to think of our domain here. What is x? X is rabbits. It is all rabbits ever. So, no rabbit knows calculus. Let C be a predicate, which means that x knows calculus. So then, how would our expression be, or statement be expressed in mathematical notation? Our original statement reads, the negation of there does not exist a rabbit such that that rabbit knows calculus. The negation of the existential quantifier of x, C of x. Of course, now if we were to negate this original expression, we would just remove the negation symbol entirely. And then we're done. How do we express this in simple English? Well, we would say that there exists a rabbit that knows calculus, right? That would be the negation of this statement. Every bird can fly. Our domain is all birds which have ever existed. Every bird can fly. So we have that every keyword. So we have an existential quantifier before the x, all x, and then we need to create a predicate, of course. F of x is defined as x can fly. For all x, f of x. This sentence would translate directly to this mathematical statement. Now we have to negate it. But we have to take the negation, just like the question wants us to, and make sure it's not to the left of the quantifier. So we negate the universal quantifier, and we negate the predicate. There exists an x, not f of x. And we're done. How would this read in English? There is a bird, or there exists a bird, or there is at least one bird that cannot fly. There is no dog that can talk. Well, what's our domain? X is dogs. Let's create a predicate. T of x is defined as x can talk. what does our statement look like now? Well, we have there is, so we use a universal quantifier, but there is no dog, so already we have a negation symbol. There does not exist an x such that p of x. And to negate this, like the question asks us to, is easy. We just remove the negation symbol, and then we're done. In English, this would read as, there is a dog that can talk. Part E, there is no one in this class who knows French and Russian. Okay, so for this one, we might even need two predicates, but we begin with the domain. X is people in this class. Let's say that f of x is defined as x knows French. R of x will be defined as x knows Russian. So how would this look like in mathematical notation? Well, there's no one, which means there does not exist an x. There's nobody in the class who knows French and who knows Russian. So what does the negation of that look like? Well, the negation is just removing that negation symbol, and we're done. How would this read in English? There exists someone in this class who knows French and who knows Russian. There could have been many ways to express this, right? So we could have also expressed it as follows. We could have instead used a universal quantifier. For all x in this classroom, x does not know French or does not know Russian. We could have also expressed this statement with the following mathematical notation. And then to negate this, we would have had to apply the negation. We would have converted the universal quantifier to an existential quantifier. Then we would have had to convert everything in this part of the expression. We would have had to apply that negation to it as well, kind of like in De Morgan's law. So this negation of f of x becomes just an f of x. This or operator becomes an and operator. And this negation of r of x becomes just an r of x. And we can see that we're left with the same negation, even if we would have started with the existential quantifier. So we are left with the same solution, and in English it would read the same way. There exists someone in this class who knows French and who knows Russian. So I really, really do hate word problems. 1.5.8. Let Q of x, comma y be student X has been a contestant on quiz show Y. And then yada, yada, yada. It's the same thing we've been doing all this time. It gives us the domain. X is all the students at your school, and Y is all of the quiz shows on television. So in some ways, this is actually easier because they're giving us the domain, they're giving us the predicate. In some ways, it might be harder. So the first problem reads, there is a student at your school who has been a contestant on a television quiz show. We want to convert this. Well, there is, so we know there's an existential quantifier. There is a student at your school, that's the X, who has been on at least one television quiz show. So there exists a Y, which supposedly he has been on. And because he's been on it, Q, X, comma, Y. So for some X and some Y, Q, X, comma, Y holds true. Part B, no student at your school has ever been a contestant on a television quiz show. So we see the word no student, so we might use the negation of an existential quantifier. There does not exist an x for which there exists a y such that q, x, comma, y, right? There does not exist a single student at your school who has been on even a single quiz show. If instead this existential quantifier were a universal quantifier, which, right, it kind of feels like you want to make it a universal quantifier, then instead this statement would be no student at your school has ever been a contestant on every television quiz show, right? So that's very different than saying that no student at your school has been on even a single quiz show. So therefore, this is the solution. Now we could have also expressed this statement using universal quantifiers, and the solution is a little different, but ultimately it means the same thing. For all x and for all y, not q, x, comma, y. That is to say, for all students at your school and for any quiz show on TV, no student has been on any television quiz show. So you can also see it that way. I think that's a little more confusing than the other way, but either way would have worked. There is a student at your school who has been a contestant on Jeopardy and on Wheel of Fortune. So again, the key word there is, so there's an existential quantifier. There is a student. That student has been a contestant on the quiz show Jeopardy. And that student X, has also been a contestant on quiz show Wheel of Fortune. And we're done. Okay, so the final problem, 1.5.17. Express each of these system specifications using predicates, quantifiers, and logical connectives. It reads, every user has access to exactly one mailbox. Now we create a predicate. P, U, M is defined as U has access to M. Then we say that for all U, that is for all users, there exists exactly one, that's the exclamation point there, there exists exactly one mailbox where the user has access to that mailbox. Does that make sense? For all U, there exists a unique M such that P, U, M. Now, some mathematicians will accept that, this little existential quantifier with an exclamation point, it defines uniqueness, that there can only exist one M for, whatever. But if we want to express uniqueness more explicitly, right, in some places, this existential quantifier with an exclamation point might not be accepted. So to do that, we would have to have a much longer solution. So, I'll just show you just so you see how it looks like. But by all means, if you can, please use this uniqueness quantifier. It would be totally okay for you to do that. So, for all users, there exists at least one mailbox where the user has access to the mailbox. And for all n, we create a new variable here. For all n, where n is not equal to m, that is to say that that mailbox n is not equal to that mailbox that the user has access to, this implies not p, u, comma, m. For all mailboxes n, which are not equal to m, if there's a mailbox which is not equal to m, then the user does not have access to that mailbox. So this is kind of another way of representing uniqueness. I had to really think about this. So if it doesn't make any sense, you can sit here and kind of look at it for a while until it kind of starts to make sense. But definitely do not have to really understand that super well. This would be totally okay. There is a process that continues to run during all error conditions only if the kernel is working correctly. So for this one, I already went ahead and wrote the predicates. There are many ways we could have crafted our predicates to arrive at some solution, but I think this is the easiest way. Let's define s, x, x to be x has status y, and h of e to be error e is in effect. Now I know that when we create a variable, usually in the past we've always made a domain. I think just like on the problem before, I think it's pretty obvious what the domain is here. Like here, u was obviously user, m was obviously the mailbox, so we didn't define our universe of discourse because I think it was obvious. But if it's not obvious, it's always good to define it. Here though, of course, the domain is actually listed in the predicate itself. So y is the status, e is defined to be the error, so that kind of helps. But let's represent this error in mathematical notation now. There is a process, so there exists a process that continues to run during all error conditions. So for all error conditions, we have an implication. If that process is running, then this implies that the kernel has the status of working correctly. All of this is holding true at the same time that any error, the error e, is in effect. And operator HE. Okay, well, I hope this recitation helped you in one way or another. Maybe it didn't. That's okay. But don't forget to take the quiz, which should be available like sometime Tuesday, and then you will have 1 week to do it just like last time.